So there's two main problems we're going to look at in lesson 4.2. And we're extending the idea about compound interest to apply to other situations. So bottom line is the formula that we're going to extend is our future value for a yearly compounding, which was take your present amount times 1 plus r to the power t. So we're going to use this in two other situations. So in the previous recording, I went over how to apply this to raises for a job if you have a % increase in your raise. So here we're going to take a look at one, car depreciation is the first problem. And then two, a disease outbreak. And you may remember I gave some data on COVID-19 a while ago and asked you guys to play around with a linear increase in the COVID numbers. So for example, Coos Bay in May had 30 cases, and in August they had 90 cases. That's an increase of 20 cases per month. Based on the May number and the 20 increases per month, I predicted there would be 190 cases in January. Well, it turns out that in January in Coos Bay, there were almost 900 cases. So my summer estimate of 20 cases per month was different than what happened over the winter months getting us into January, right? It was way more than 190 cases, which was the 20 case per month increase. So what I did here is I changed that 20 increase into a % increase. And the way you change a fixed increase into a % increase is you just take the change, which is the 20, and you divide by the starting number, 30. I'm going to write this down on my paper in a minute. So take the change, divide by the starting amount, that gives you % change, and 0.66666 is about 66.7%. So if we looked at the monthly % change over the summer, that was more like a 67% increase per month. If we let that 67% increase keep going through September, October, November, December into January, then that % increase predicted there would have been almost 2,000 new cases, total cases, excuse me, in Coos Bay. But again, the actual amount was only about 900. So the rate of growth of COVID cases in Coos County was somewhere between a straight line and an exponential curve. Okay? This one underpredicted the straight line, this exponential curve overpredicted. So we're going to apply this same idea to a couple of other situations. All right, so where'd you go? There you are. So let's do the car depreciation first, and then we'll do the disease outbreak. So again, I'm focusing on the formula F equals P times 1 plus R to the T. And the situation here is I have a new car that costs $26,000. And it's losing value each year, right? You get a new car, as soon as you drive it off the lot, it's worth less, right? Because it's not brand new anymore. A year later, it's worth less than that. 2 years later, it's worth less than it was a year ago, and so on. So it's losing value. And that losing value is also called depreciation. And the value that we're losing is 15% per year. Now, since we're losing value instead of gaining money, right, like in a savings account, we're losing, that means our rate, R, is negative 15%. So negative rate. 15% is a decimal. Remember, the percent symbol means divide by 100, so this would be negative 15 over 100, which is negative 0.15. Applying this to my formula here for the future value of the car, I'm starting with $26,000, and then I have 1 plus my rate, which is a negative, so I'm going to do a minus 0.15. and then T would be the number of years. Now, I can actually clean this up a little bit because I can subtract 0.15 from 1. And if you do that, you're going to find out that that's 0.85. And then tell me if this makes sense when I explain it. 26,000 times that to the power T. Now, order of operations here, I got to do the exponent before I can multiply, so I can't clean this up anymore. This is as simple as it gets until I plug in a time for T. Now, 0.85 is 85 out of 100, right? 85 hundredths, which is 85%. So does this make sense? If I lose 15%, don't I get to keep 85% of the value of the car, right? So it loses 15% per year, but we retain 85%. And that's what this formula tells us right here, that each year, we keep 85% of what it was worth the year before. So that if somebody says, okay, what's this worth 5 years later? So after 5 years of owning the car, so at the beginning of the 6th year, it would be 26,000 times 0.85 to the power 5. So I can just plug in any amount of years that I want there. Calculate that on a calculator. 26,000 starting point times 0.85 raised to the power 5. And so this tells me in 5 years, it's only going to be worth less than half, 11,536.34. So that's the value of the car 5 years later. And if you say, hey, how about 2 years later, what's it going to be worth? Well, I just put a 2 there and see what it's going to be worth. So if I go back to my calculator, 26,123 times 0.85 raised to the power of 2. After 2 years, it's worth 18,785. So you pick a year, I can tell you what it's worth. This depreciation is never going to be completely zero because we always keep a little bit of the car value behind. And when I was a teenager, I used to work at a used car lot. And the guy that ran the lot said, anything you can sit in is at least worth $500. Now this was back in the 80s. So I don't know if that's still the case, probably more than 500. Okay, so that's the car depreciation problem. It's an extension of our compound interest problem. And the key here is that rates can be negative, in which case we subtract from 1 instead of add to 1. So 1 is the base, 100% means what did you start with? That's what the 1 represents. All right, Ebola cases is the next problem. So Ebola is a virus that really messes with your mucous membranes and blood, and you kind of bleed out. And people survive it, but it's pretty rough. It's got a pretty high mortality rate. It doesn't spread as fast as COVID, but it spreads pretty fast when it is out there. So here's the situation on Ebola. In April 2014, there were 130 cases. And then a month later, so it's after April, May, in May of 2014, there were 234 total cases. And these are totals, not just monthly cases, so total cases. So from here to here, there was an increase of, what would that be, 134? So over 1 month, there was an increase of 134 cases. So this is kind of like the COVID data that we looked at before, but it's slightly simpler in that only 1 month went by. So the slope here right, for a line would be our M is just 134 over 1, which is just 134.
I got 104.
Oh shit, I can't subtract. Thank you so much for fixing my subtraction.
You're welcome.
Thank you. Yes, that 3 subtracts out, doesn't it? Glad you caught that. All right, so there are 104 cases increased in that month. So we're just gonna kind of assume, all right, well, maybe it always increases by 104 cases per month. So if we were to do something like let T equal the number of months after April, then the linear version of this would be that the total number of cases is equal to an increase of 104 cases per month. So that's our slope times T. So like our Y equals MX. Plus, since T is months after April, we would be starting with 130 cases. Okay? So starting with 130 cases, we're increasing by 104 cases per month. Okay? So if T is months after April, then this is our Y-intercept, our B. We have an increase of 104 cases in 1 month, so that's our slope, 104. So this would be the linear version of it. All right, but not everything increases at a constant rate like that. It could be there's a percent change here. So what about percent change? And just a note, this idea of slope here is also referred to as an absolute change. It's referenced that way in this lesson, and this goes back to Math 62, the previous course. When we look at percent change, another name for percent change is relative change. And that's kind of what I looked at in the previous example when I looked at the COVID cases. Percent change is always the absolute change divided by some original amount. So for us, our percent change is 104. Our original amount was the 130 cases. So I need to see, okay, what's 104 divided by 130? That's going to be my percent change. Let's whip out a calculator. Figure that out. 104 divided by 130. And I get, oh, I did something wrong. I missed a button. 104 divided by 130. There we go. I get 0.8 or 80%. And double check that. So that equals 0.8. Now remember, to convert a percent to a decimal, we divide by 100. So to convert this into a percent, we would take that 0.8 and multiply it by 100%, which gives us 80%. So that's an 80% increase from April to May. And so another way to think about the situation, okay, if it doesn't increase by 104 cases per month, maybe it increases by 80% per month. And this is, again, still a per month number, but it's a percentage instead. And this 80%, that's the R in our compound interest formula. So for relative change, so Ebola, relative change, percent change, again, relative change, percent change mean the same thing. We just calculated that the R, the rate of change, is 80%. The formula for percent change is pretty much the future value equals the present beginning value times 1 plus R to the power T, right? This is our basic yearly compound interest formula. This time, instead of doing years, our T is going to be months, because we're looking at monthly change in Ebola. So then the future value for Ebola, in this case, would be C equals, starting with 130 cases, right, the April amount, we take our 1 plus our percent change, 0.8 as a decimal, to the power T, where T is our months. Now, we can, 1 plus 0.8, we can clean that up. That's really 1.8. So we can also write this as 130 times 1.8 to the power T. So we have two different versions of the formula. We have a linear or absolute version of the formula, and then we have the relative or percent compound interest version of the formula. And they're different, right? So this one, again, is the relative percent change versus the linear one, which was C equals 104 cases per month, starting at 130. And so then the next thing we're gonna do is we're just gonna kind of play around and plug some numbers in and see what happens. Like what happens 6 months later? What happens 24 months later? So let's put some of those in here. So I'm gonna make a table, months later. And we already know that 1 month later, there were 234 cases. And if we plug 1 into either of these formulas, we should get that 234 back. So I'm just going to double check that. Remember that 234 was given to us for the next month. So if I take my 130 times 1.8 raised to the power 1, there's my 234 from the exponential relative model. If I take my 104 times 1 month plus the 130, that's my linear version of the formula, 234. So next thing we're going to do is we're just going to say, okay, what about 6 months later? What about 24 months later? So 6 months later, 24 months later. So 6 months later, it would just be 130 times 1.8 to the power 6. Whip that out on our calculator. This one would be 104 times 6 plus 130. So we'll have to whip that out on our calculator. Similarly here, and again, this would be a nice place for a spreadsheet, huh? Because we're just repeating the same calculations with slightly different numbers. 130 times 1.8 to the power 24 equals what? And 104 times 24 plus 130. I need to calculate each of those. So whip out your calculator, get those numbers. I'm going to do it in a spreadsheet this time instead of the calculator. And I probably should make a new spreadsheet instead of my COVID one, but it's easy, it's here. So let's see, we got Ebola months to keep track of. We have our exponential one. Exponential is also what we call relative change. Linear one, which is also called absolute change. From, I've got, let's see, 0, 1, 6, and let's see, was the other one 24 months later? And I'm just going to use the formula. So this one is 130 times 1.8. It's my exponential raised to the power, whatever number of months is next to me. I can fill that down. Whoa, 24 months later is a lot. Interesting. Linear, that one is the 104 times the number of months, plus starting at 130. And once I type that in, where I reference the month number here, I can click back on it and fill it down. All right, and let me put some commas in this. Now, I'm gonna round these to whole numbers because this is people and you can't have a fraction of a person. So a couple things I'm gonna do. Let's see, I wanna format it. with commas and then get rid of the decimals. Oh my gosh. So the exponential one says that if Ebola keeps growing like it was in the first 2 months, then there's going to be almost 200 million cases. Wow, that's crazy. I don't think that happened. And then the linear one says, and if it keeps growing only by 104 cases per year, then it's going to be more like almost 3,000 cases. So you get pretty different case numbers from the exponential model to the linear model here. So kind of looking at this, which one might be a more accurate representation of what was going on? Well, eventually they controlled the Ebola virus back in 2004 in West Africa. I mean, Ebola is still around, people still get it, and there are outbreaks, but it definitely didn't grow by these numbers right here. Like I don't think there were that many people in West Africa. I don't know what the population of West Africa is, but I seriously doubt there were that many. So I think the linear model might better represent this situation than the exponential one. All right, that's it. That is lesson 4.2 in a nutshell. All right, so we went over the two main problems. I answered all the questions that you need to answer. So just hopefully you took good notes there, or maybe you were trying to multitask and follow me and fill out the lesson at the same time. In the first recording I did, I went over a few different examples of compound interest, and I extended it to relate back to simple interest with that job scenario. So here I had the 4% per year raise versus the $2,000 per year raise. And we could see that although the $2,000 seemed like a better deal for a while, right? It paid more. So this was the difference, how much more the fixed was. Eventually, the percent raise did better. And then after that, it was always better. And you can see in a similar but more dramatic example, this exponential is like the percent raise. Remember, relative means percent. And this absolute linear thing is fixed. Notice the exponential way outcompetes the linear one. And that always happens. Exponential functions always outcompete linear. Reminder, we looked at these at the beginning of the course when we were playing around with different graphs. This was also looked at briefly at the end of Math 62. When you graph linear stuff, it lines up somehow. When you graph exponential stuff, you get a hockey stick type shape is the way I describe it. So exponential, there we go. So if we graph something that's exponential, what happens, although it starts off kind of slow, it eventually takes off and it gets steeper and steeper and steeper, right? So again, imagine like this is a hill you're climbing, the linear hill here, it's always the same steepness. Exponential hill gets steeper and steeper and steeper, and it's almost vertical eventually. It never gets totally vertical, but eventually you're climbing a cliff, right? So the point is exponential, although it starts off slow, really shallow, like I'm hiking here, I'm like, this is nothing. But then all of a sudden it's like, oh my gosh, I can't continue, it's too steep. Exponential always beats linear is the moral of part of the story of today. All right, so I apologize that I have to end class early today. You have everything you need to do the lesson, and some of the examples cover homework problems you're going to see today. If you have any questions or you're working on your homework or your lesson later, just message me through the homework system or through Canvas, and I'll get back to you as soon as I can. And that is it.